So, in our last class we were discussing on the process control block or PCB. So, as we said previously that when a process is executing, so it has got certain snapshots from the memory, and those snapshot information is very important because so if we are if we have to suspend the execution of the process for some time and we want to restart it later, then the same environment has to be given. For example, if I say that I have got a piece of program which is consists, say this is the program that we have, and this program has got several lines in it. Now, so maybe at present we are at this line of execution at which some requirement came from the system so that this process has to be suspended, and some higher priority process that has started, that has come, so that has to start. Then what happens is that after that higher priority process is over, I must be able to come back with execution of this particular process, and it has to start from this point onwards. So, it cannot be from this. Now, the things that we need to remember at this point, so that we can restart from this, one is the program counter value for the process, and also when a process is executing, it may have a number of variables, and some of these variables are allocated space in the global data segment, and some of them are allocated in the local data stack, and some of them are allocated into the CPU registers. So, as far as the CPU is concerned, this program counter plus CPU registers, so these are important. And if this particular program, so it has been given different parts in the memory, maybe in this is the code segment for this program. So, this is the data segment for the program, and this is the stack segment for the program. So, it may be like this. So, I need to remember the regions of the memory which has got this code, data and stack for this particular process. So, at this point of time, so what are the code, data and stack segment limits for this particular program, that has to be remembered, so that later on when the process comes back, so we can again set these limits, and we can load appropriate CPU registers that needs to know the values of these limits, and the program counter and the CPU register. So, all those values can be restored. Now, how do you remember all these things? And this program control block or PCB comes at this point, comes to help in this particular situation, because when I am suppose I have executed up to this and then I have to leave the CPU, then this program counter, CPU registers and this memory limits, similar they are remembered. Similarly, if the process has opened some files, then this list of open files is also remembered. So, many other information will be required, and which information we should put in the PCB. So, that is a bit designer specific. Like some OS designer may feel that some information should be kept in the PCB, whereas others may feel no, it is not necessary. But in general, these are the most important things that we have. One is the state of the process, then the process number. So, this is very commonly known as PID or process identification number. So, this is a very important and unique number for every process. This PID is unique, and whenever the process is created for the first time, that is it is in the state new. So, this PID, one PID is assigned to the process. So, this way this process control block will have this information. It also keeps some more information like this CPU scheduling related information. Like I may have a policy that if a process is coming from say user 1, it will have a higher priority than a process coming from user 2. So, for the scheduling information I should have this priority information available. I can also have a policy like this, that if a system is using lot of CPU space, CPU time, then its priority should be low compared to a process which uses less CPU time. So, this is basically giving a priority to a interactive program than a computation oriented program. So, interactive program means, so it will be taking lot of data from the user or the file, etc. So, that way it has to given priority, because otherwise the user will feel that the system is not doing my job. So, this interactive jobs, they definitely have higher priority than these jobs which are computation oriented jobs. So, like how do you know whether a task is interactive or computation oriented? So, that is basically done by monitoring the how much time the CPU is being used by the process. So, if the CPU is if the process is given CPU for 2 seconds and we find that the process has used entire 2 seconds without going for an IO break. So, that means the process is a compute bound job, and if it is the other way, that is out of this 2 seconds maybe it has executed for 0.1 second and then it has gone for an IO break, that means it is an IO oriented job. So, that way this information has to be stored. Now, where to store this information for the process? Naturally PCB is the answer. So, we can keep this CPU scheduling information into the PCB. Then memory management information. So, what are the memory locations allocated for this particular process? So, that is important. So, how much, because many times we need to protect the memory space so that it is not accessed by other processes. Many a times we need to have some charging corresponding to that memory usage. So, if a process uses more memory, so it will be it has, the user has to pay more for the information. So, that way we can have some memory management related information like memory allocated to the process. Then some accounting information. So, accounting information like the CPU, how much time the CPU is used, what is the actual clock time from the start time, then time limits. So, like that, maybe some processes we can start only at some particular time. For example, if there is some batch job, maybe the batch jobs they will be done at night only. So, during daytime we are running only the interactive jobs. So, this type of time limit, time related information, so they should be kept into the PCB. So, this accounting information is kept. Then the IO status information. So, IO devices allocated to process, then list of open files, etc. So, they are to be remembered because so if you have got a process which has opened a file, then if some other process also wants to modify that file, then that should not be allowed. Even if this process is not executing now, so so the files that are captured by, that are currently opened by this process should not be given to other processes to access. So, we should have a note of the list of open files for the current process. So, in this way this process control block, so it holds the majority of the operation, majority of the information that we need for running the process smoothly. So, and if we want to switch from one process to another, then this PCB is going to help us in a big way. So, all operating systems they maintain PCB in some form or the other. So, next we will be discussing something on threads. So, we will be coming back to these threads in more detail later. So, in this particular slide we just try to understand some concepts about thread. So, process has got a single thread of execution. Now, what is happening is that if for example, the roots of a quadratic equation, that program. So, if these are the program execution lines, so it starts from one end and goes to the other end. So, there is only one thread of execution. So, for this type of programs we cannot have different requests, but consider the situation where I have got a web server, and this web server, so different users, so they are sending requests to this web server for different pages. Now, if the web server does it like this, that it takes the request from the first one, then it processes it and then it goes to the request for the second one. So, if it does like this, then the person who has at the end, so they will feel that okay, my requests are not being served. So, what this web server does instead is that this web server, so it creates a thread that takes care of this particular request. Similarly, it creates another thread that takes care of this. So, this has got the advantage, because even if this thread is due to some problem or the other, this thread is halted or this faces some problem. So, other threads, so they will continue. So, that way we have got this thread based design. So, we have got so within the same program we can have multiple execution sequences. So, this process has got the process till now we have got a single thread of execution. Now, if I have got multiple program counters per process, so each thread is executing the same routine for this web browsing, but this thread may be executing in this at this location, while the second thread may be somewhere here, third thread may be somewhere here. So, they are at different program counter values. So, these multiple locations can execute at once and multiple threads of control. So, they are called threads. So, need storage for thread details and multiple program counters in PCB. So we need to augment the PCB structure where it keeps a note of the threads that are currently there in the system for this particular process, what are the corresponding program counter values and what are the corresponding CPU register values. So, they are to be remembered. So, we will come back to this thread discussion in detail later in our later part of our course. But as far as PCB is concerned, for every thread I have to have some information stored in the PCB of the process. Now, if you look into this Linux operating system, then this process representation is by means of a structure called task, and this structured task, it has got a number of components in it. One is the PID, task PID, which is a unique number. So, it starts with 0 and goes on increasing to a maximum value, and then it comes back to some 0 again. Then we have got a long variable state. So, it is the state of the process. Then we have got the time slice for scheduling information, how much time slice if the process is given CPU, then for how much time it should be given, and there may be different depending upon the priority, this time slice value may differ. Some process we may want to give less time slice, some of them we want to give more time slice. So, that information may be coming. Then we have got this parent of the process. So, particularly in Linux and Unix operating system, we have got this concept of hierarchy, and there is a parent child relationship between the processes. So, we have got the first process which is known as the init. Okay. So, this is the first process created, and this is process PID is 0, and all other processes, so they are created from this init process. Okay. So, any process at any point of time, so it can create a new process, and then that new process can again give rise to a number of new processes. So, we have got this parent child relationship. So, if this is the parent, we have got this as the child, and for these processes this is the parent and they are the children processes. So, we have got the parent child relationship between the processes. Now, if this parent dies at some time, maybe after due to some erroneous situation, suppose this parent dies, then what happens to this child which become orphan? So, what this Linux or Unix says is that this becomes now a child of the init process. So, that way we have got a parent child relationship, and this we have got for every process we remember the parent and the children list. So, this is the current process. So, this is the currently executing process. So, then we have got this we have got the task chain actually. So, these are the task chain, this is the task chain. So, we have got all of them are put into a chain like that. Then we have got this children, they are put on a list. Then we have got files, list of open files, and address space for this process, this structure So, this way we have got information available in the Linux operating system. So, other operating system will also have similar such structure. So, if you look into say Windows or any other operating system, so you will find that the similar such process structure is maintained, PCB structure is maintained. Now, process scheduling. So, this is a very important concept, because we have got at any point of time a number of processes which are ready for execution, and this operating system it has to decide like which process should execute next. Okay. Now, how to do this? So, what are the objectives behind doing this process scheduling? One is definitely to maximize the CPU usage. So, we will like to have this CPU utilized for 100% time. So, but this 100% time is often not possible, because maybe one process was given CPU, so it executed for some time and then it is asking for some IO operation. So, when it asks for IO operation, so we have said as a general policy we put the process into a blocked state and we take up another process for execution. But in between what happens is that putting this process out of CPU and taking the next process into the CPU, so that takes some time. So, that time the CPU is not being properly utilized. So, we say that this switching, if it is can be made very fast, so then this time will be less, and so we can maximize the CPU time. So, if one possibility is that we can do a scheduling so that this number of switchings will be less, and other thing is that we can make these switchings faster, so that the time needed for a particular switching is not much. So, we can maximize the CPU usage. So, by quickly switch processes onto CPU for time sharing. So, process gives up, then CPU under gives up the CPU under two condition. One is the IO request, that I have already said, that there is some IO operation and that has to be done, and after n units of time have elapsed. So, there may be a timer, and then after it is the CPU, the process was given some time slice for execution, and after that time slice expires, the process is taken back from the CPU, and so that way the process can give up CPU. And once the process gives up CPU, it is added to the ready queue. So, once it gives up, so it is joining the ready queue, and if it is waiting for some IO event, so it will join the IO event queue. But anyway, the process will be put into a queue again. And this process scheduler, it has to select among available processes in the ready queue for next execution. So, you can ideally see it like this. So, if this is that ready state, and this is the running state. Now, this CPU this scheduler, so you can say that there is a queue associated with this ready. So, any process which is joining in the ready queue, so they are actually joining this queue. Now, depending upon the priority of all these jobs that we have in the queue and other scheduling related parameters, this scheduler, so it will pick up one particular job from this and it will put it into the running state. So, that was the dispatch process. So, the scheduling decision has to be proper, so that the process is taken from the ready queue and it is put onto the running state. So, this way there can be different types of scheduling queues. So, this OS maintains scheduling queues of processes. So, we have got job queue, set up all processes in the system. So, whatever processes are there in the system, so everything is there in the job queue. Then there is a ready queue, which is the set of all processes residing in the main memory and ready for execution. So, they are otherwise ready in the memory. So, if they get a chance for execution, if they get the CPU, then they will the process will execute. So, they are put onto the ready queue. Then we have got device queues. So, device queue, so they are set of processes waiting for an IO device. So, for example, maybe there are requests to the disk and there are many processes which are requesting to the disk. Now, disk being a semiconductor, this is being an electromechanical device. So, it is not as fast as the semiconductor devices. So, as a result, it will take some time to service those requests. So, the disk head, it needs some time to go from one sector to another sector, from one track to another track. So, that way it requires some time. So, the processes which have requested for this IO operation, they have to wait. Okay. So, this waiting time may be variable depending upon the type of resource that we are talking about and the load on that particular device. How many users are, how many processes are waiting for accessing that particular device. So, these device queues will be there, and processes, they migrate among various queues. So, initially the process, when the process is created, so it is put into the job queue. From there, when the process has been has got the CPU, got the copied onto main memory, it comes to the ready queue, and then from the ready queue, so depending upon the scheduling, so it may go to the running state, or after running for some time, it may join the ready queue, or it may request for some IO operation and join the corresponding device queue. And from the device queue, if the job is taken up for IO satisfaction and the IO operation is done, then it will be joining back to the ready queue, and that way it goes on. So, that is why a process can migrate among different queues in the system. So, this is the ready queue and various IO device queue. So, ready queue, we have got this this PCB 7 and PCB 2. So, these are the two processes that are there on that are now ready. Out of that, this PCB 7, so that is process 7 is the first process in the queue, and this is the PCB 2 is the second process in the queue. So, they are there. Now, maybe we have got magnetic, for the magnetic tape device, there is no such process which are waiting for this magnetic tape, the tape unit 0. Magnetic tape unit 1 also there may be nothing. then the disk unit 0. So, we may have got a number of processes which are waiting for this disk, like process 3, process 14 and process 6, and for the terminal access maybe process 5 is in the queue for doing this thing. So, this way we can have at any point of time. So, if you take a snapshot of the system, then the device different queues may have different processes waiting for the queue, waiting in the queue. So, a typical queuing diagram that represents the process scheduling is like this. So, initially a process is in the ready queue when it is when the process has been copied into the main memory. So, it joins the ready queue. From the ready queue, eventually the scheduling will be done. So, this particular arrow means that the process has been scheduled. So, it gets the CPU. So, when it gets the CPU, so it will be executing for some time, and it may so happen that the process gets over and it goes out of CPU and that is terminated, or it may so happen that process has come across different situations, like it may request for some IO operation. So, in that case it joins the IO queue. Okay. So, this is one possibility. Another possibility is that the time slice has expired. So, if the time slice expires, then the process is taken out of CPU and put onto the ready queue. So, this is the other operation. Then what happens is, so maybe one process when it is executing, it creates another process and then it waits for the execution of the child process. So, this is a typical situation that we have got in these command line interpreters that we have in any operating system. So, when the process, so if you give a command for execution, then the shell program that we have, so it has to wait for the command for the child to be over. So, this child executes, and so after the child finishes, so this process joins onto the ready queue. So, this is one possibility. Then we can have this interrupt. So, there may be an waiting for some interrupt to occur, and when that interrupt occurs, it goes back to the ready queue. So, this way we can have different type of situations in which the processes may be executed in some sequence, and accordingly they go through different queues and different scheduling stages in the system. So, this is a typical example how this CPU will switch from one process to another process. So, this is this is known as context switching. So, this is known as context switching. So, what happens is that this is one process that is there. So, process P0, so it was executing. So, process P0 was executing. So, this is by a particular snapshot of the system, and then some interrupt or system call has occurred. So, it goes to the kernel mode in the operating system, though it will save the state of this process 0 into PCB 0, and then process P1. So, after some, so this is there. So, now the scheduler will come and it will decide which process to be loaded. So, suppose it decides that the process 1 will be loaded. So, it will be it will reload the state from PCB 1 into the CPU registers, program counters, etc., and then the process 1 is now ready for execution. So, the control goes to process 1 and it starts executing. After some time, after the process 1 has executed, so again maybe process 1 will generate an interrupt or system call, and then when it happens, so it has to save information into the PCB 1 corresponding to process 1. Then after some time, so this now the scheduler may decide that I have to restart process 0. So, it has to that decision is taken in this part in this region of time, and then it to restart process 0. So, it has to reload state from PCB 0, and then it can give the control back to process 0, and it starts executing from this point. So, this way we can have switching between processes. So, whenever a context switch occurs, so the process which was executing so far, its content has to be saved into the corresponding PCB. Then the context from the next process's PCB has to be loaded into the CPU registers and all, and then the next process can start. So, this is known as the context switching. Now, you can understand that this is an overhead that is coming to the system. This saving the context and reloading the context. So, that is basically the context switching, and that takes the time. And so, effectively you can say that this is an wastage of CPU time. So, we will try to minimize this context switching to as little a value as possible, and accordingly the CPU usage will be going up. But definitely there is a question, like if we just reduce it to some to a arbitrary value, then it becomes more of a first come first served type of situation, and that way the overall time may be that we will see that it has got some bad implication in the system performance. So, that creates the difficulty. So, we will be talking about different types of schedulers which will take a decision like which job to be executed next. Like in the ready queue, there are a number of processes which are waiting for these jobs to be selected for execution. So, that is done by short term scheduler. Then we have got long term scheduler which will be selecting the jobs that should be executing that should be made ready for execution. So, that is the long term scheduler, and sometimes we have got a mid term scheduler also, which is not there in all operating systems. What happens is that there may be a number of processes which have completed their IO operation. So, out of that, some of the processes they should be they are put back onto the ready queue. So, that way we can have this mid term scheduler also. So, we will look into these scheduler operations in the next class.